how this bending will be. And the strategy is to decompose this bending into the y and z components. Then we apply the superposition principle. So for this case, let me get this. So right now you have the statement of the problem. Let me directly work on the board here. So for these questions, this is a cross section like this, and this is the y and z directions. And here we put the origin at the centroid of the cross section. And for this example, we have the direction of the bending. The bending basically is this. Apply our thumb to the direction of this arrow, and then this one, the four fingers, give us is the circulation of the bending. And drawing in this way is a double arrow for bending, and equal to 600 pounds per inch. And again, this direction is like this, okay? And then we decompose into two directions. Okay, we project it into y and z. So this is the amount in the z direction, so we call it mz. This is the amount in the y direction, we call it my. And by calculations, and this angle is 30 degrees, so this angle is 60 degrees. So this is 60, so this is 30. So from here, the mz equal to n times cosine 30 degrees. And this one equal to 600 times square 3 over 2. So this one is 300 square 3. And for my is the sine 30 degrees. So that is 300. So now we have the two components so on the bending, so we can use the superposition principle. And for this one,
are you going to say negative for MZ, or are we not looking at the direction?
here right now we only focus on the magnitude, and right now we try not to
so
get too much complicated. So now for this case, you see I just draw the direction, so MZ is this. And my is this. Okay, so that is the case. And now again, remember our generic formula is sigma equal to my over I. And here, if you want to use the minus, then basically sign convention go to m and go to y. If you only focus on the magnitude is my over I. Okay, like this. I want to take up this strategy. I focus on the magnitude and then justify the attributes by observation. So now for the first one, before we proceed, how about we just justify our the sign for this. For this case, what is MZ? MZ applied is in this direction. Okay, so if you would visualize, this is the cross section, and this represent is a cross section protruding from the board. So that is this. MZ is the bending about the z-axis like this. So that will be causing the beam to bend like this. At this side, the bending is bent down. So actually, the beam will be looking like this under MZ situations. Okay? So in this way, you can see in the upper portion, that should be in which? In tension or in compression?
Tension.
Yes.
I guess I'm a little bit confused in your determination of the direction, in the sense that I understand the direction at the moment.
Yes.
But in terms of knowing how the actual beam bends, what references you're using,
yes.
how you're using it.
This side, here I draw, represent is this one.
Okay.
And now the bending is like this. Bending is to bend this side like this.
Okay, that makes sense.
Okay, the other side, in balance, then we go the other way.
Okay.
Okay, so we're back to here. Then the upper portion will be in tension. The lower portions will be in compression, the tension compression. And now for this case, again, the bending MY is like this. So now this is a cross section. Bending on this side is bent like this. So for this scenario, the beam will be bent like this. And now you can see in this way, which side, right and left, which side is in tension? This one. Okay. This one, the right side in tension. So, sorry, left side. Sorry. And then this is in compression. So now for each case, we have all the things, and now we work on where is A. A is here. Okay, A is here. So now at point A. So at point A, we work on the magnitude. The generic formula is my over I. So right now you can see the m, this one is a symbolized the function for different things. So m is the bending. For this case, m is mz. And what is I? I represent is the point, the distance between the point to the neutral axis. For this example, right now you can see the bending, and again, this is the beam. The mz is about this axis. So you can see the mz is about the bending like this axis. So that should be like this. Mz about bending about this axis, and then bending over like this. So tell me the neutral axis is where? Y or Z axis? Z axis. For this case, the neutral axis for this subsystem, that is Z axis, because it's the beam like this. Okay, so now to this stage, identification, to identify the position of the neutral axis is become very critical. Okay, for this case, it's Z. So here, if you wish, you can label this is the neutral axis. And now again, back to this problem. This y represent is the distance between the point to the neutral axis. So that is this distance, right? And that is 0.75. And what is I? I, again, is the moment of inertia with respect to which axis? About the neutral axis. So right now for this one, it's about Z axis. Okay. And A is in which region? In tension. So basically, this is a magnitude. We give a plus, and that represents this is a tension. This is a tensile stress. Okay, this is for this case. And now for this one, A is here. Again, we plug into that formula. M, right now, M is the my. And the distance. So now for this case, what is the neutral axis? The neutral axis is about which the bending is applied. So now the neutral axis is y-axis. Neutral axis is y-axis. Okay. Okay, and now the y represent is the distance between the point to the neutral axis. So that is this dimension here. Is 0.25. Okay, and I is the moment of inertia with respect to the neutral axis, for which, for this case, is y-axis. And for this case, A is in the positive in the tension, so this is one positive. And now we take the superposition. So for this way, for sure, we can say A will be in tension before we do the calculation. Okay, and now we plug into the calculation and do this one carefully. So now we have this dimension here, and this is 0.5, and the height is 1.5. So this is y, this is z. So Iy is 112, and the 2 terms, and q. Again, that is a 2 dimension, go either way. This is a dimension being bisected by the neutral axis. So what is this number? 0.5. And this is 1.5. Okay, so that is the way I memorize this equation, or otherwise you can look at the formula. And Iz 112, 3, and that is about z-axis. So 1.5 is go to the cube term here, and this is 0.5. So we plug in the information here, and
Is A not on the axis, so you have to do the parallel axis here, or no?
Say that again.
Your A point is not on the axis, right? So are we doing the moment of inertia around Z, or are we doing it around A?
The A is here, right?
Yeah.
And your question is
So you're doing the moment of inertia around the actual axis?
about the neutral axis.
I thought we had to do it around A.
About the neutral axis.
That just gives us the moment of inertia of the whole body, and then that y will give us that data.
So this result, if we calculate it, that would be 7.57 KSI. I think my solution has mistake. So my solution has a mistake. So probably this number is not trustable. But anyhow, if anyone, you can implement this number quickly.
No, that's right.
That is right? Because I noted the sign.
Well, it's 757.28 pounds,
Okay.
so yeah.
Because my this is not my solution. The solution from the textbook, it got the wrong sign on this term. I'm not sure. Anyhow, if this is right, then we take this one. Okay.
Yeah, that's right.
So now this is point A, and now we look for the point B. And for the point B, the same thing. Let me use this one, and probably you can quickly draw your things. Your B is here. Okay, now we change the B. So now for the B, we simply need to re-identify the whole things here. Okay, now for this case, and again, the bending is MZ, B is here, and this is the distance from the point to the neutral axis, so which is the same 0.75 inch. And the same thing, I about the z-axis, the same thing here. And B is in tension, so positive. Now for this case, B is here. And this one represent is from the point to the neutral axis, and which is y, so that is this amount, and that is 0.25. Right now for this case, the B is in compression, so this one we added up is minus here, representing compression. And this is a superposition of the two cases. So with plus is basically is a positive term minus a term here. So this number will be becoming, would that be minus 2.03? Sarah? Will that be this one?
Yeah.
I remember her name.
I'm gonna check.
Okay. Okay? Yes.
Your Z value is positive. Your 0.75.
This, again, here I take up the magnitude, so everything in the magnitude expression should be positive. Here the y represent is distance. Distance is always positive. Okay? So again, I take a strategy is this. I try to separate the calculation of the magnitude from telling the sign. Telling the sign is from here. So here, when we talk about the magnitude calculation, you take everything is positive in the calculation. For the sign, we can justify by their location. Okay? Okay.
And that number is correct, yeah.
Correct. Thank you. And now, any other questions about the A and B? And I can tell you that D, at point D, basically the D is opposite to A. And you can verify at D, the stress at point D will be minus 757 KSI. And you can double check with this one for your own exercise. Basically, D is the anti-symmetric to A, okay? And now, any more questions about this? So now, if no questions, I'm going to use the same example to ask the questions. And where is the neutral axis for this problem? For the problem under, we call it unsymmetric bending. So which means the neutral axis is for the combined case. For the individual subsystem, we know the neutral axis for subsystem is like Y or Z. But now I'm looking for is for this one. And again, the neutral axis is where, with by definition, zero stress. And the neutral axis always is a straight line on the cross section. So which means you can see here the ABD, here you can do the combination. So as long as you can figure out something, and then you can use geometry to make a straight line. And that could be one way. Otherwise, we can try this way. Let me redraw this one again. Okay, this one is the same as we had before here. And now, again, for this case, here is upper portion is tension, this compression, and this is tension, compression. And now, again, for definition, is the neutral axis is where the stress equal to zero. So we're simply looking for the collection of the points in this cross section which has a zero stress. Okay, before we do this one, you can see the result of this one is a combination of the two, right?
Is it going to be two variables?
So you can see here, for example, here is the we using YZ, we have 4 quadrants. So zero stress would be only possible